Okay, so that means if you have any solutions of these kinds, phi of x, it can be written in terms of a to the power 3x. It is something like that, or some suitable choice of these constants, I mean C1 and C2, right? So now, if you substitute this here, does it satisfy the equation? Can you check?
Yes, sir.
Yes, sir.
Yes, sir.
It satisfies, right? Probably otherwise I won't have, wrote this in here, right? Okay, fine. So then, like, say, can you tell me, it doesn't look like it is in this form. Why it still satisfies?
Because sine hyperbolic 3x is e to the
It's
power
nothing
3.
but a linear combination again. Linear combination of this, right?
So this is
if
minus,
you
sir. E to the power 3x minus e to the power.
It is minus. Cos was. Is it minus or plus?
Minus. Plus for
Minus.
cos.
Fine. So if you substitute it here, it is definitely going to give you a combination like this. Okay, fine. So that is the reasoning behind that. This is also a solution. Okay, so here you have seen an evidence that any solution of a given differential equation, it can be expressed as a linear combination of d, not d, not d, of a fundamental set of solutions. Okay, I'll tell you why it is not d. Okay, fine. So, okay, so I'm almost done with the slides here. And the second one is pretty straightforward. Again, it is a linear equation with constant coefficients. You'll be able to find out the auxiliary equation and hence the roots of those auxiliary equations. And from there, you'll be able to find out a linear combination, right? So, okay, let's not spend much time here. So now, let us come to a non-homogeneous equation. Let us come to a non-homogeneous equation. Fine. So, okay. So now, consider this equation again. B and y. Dxn. I'm just going to okay, fine. Consider this, okay, and then what is going to happen? I can consider its homogeneous counterpart by simply plugging in 0 on the right hand side, right? 0 on the right hand side. Okay, say suppose let me call it 2, or maybe let me call it 1. Okay, and let the homogeneous counterpart of this, let me call 2. Okay, although I haven't written it, this is simply 2 is simply when this is equal to 0. Is it okay? Fine. Okay, so then if I can find n linearly independent solutions of this homogeneous counterpart, right? Given by say y1, y2, yn, y1, y2, yn. So then definitely your say yz, this is equal to c1 y1 up to cn yn. It is going to be a general solution of 2. Is it okay? Fine. Now, say suppose yp, so this is ygx, so this is simply y1x. Okay. Suppose your ypx this is a particular solution. This is a particular solution of the non-homogeneous equation 1 state, right? So that means if you plug in here, or maybe should I write it as maybe I see this equation rather than writing it like this equation. I can write it like this also now. So then you know what is the meaning of LD. Okay, the linear operator D. You know what is the meaning of that. Is it okay? Fine. Rather than writing it all the way through, let me shorten it. Okay. So that means if ypx is a particular solution of this equation, so that means you are going to get your LD, your ypx. This is equal to g of x. This is equal to g of x. Is it okay?
Yes, sir.
Yes, sir.
Fine. Fine. Okay. So now if I plug in, say this one, I mean yzx plus ypx in this equation. So then what is going to happen? What is going to happen? Like say your LD, if I operate this with this, so then this is going to give me LD your yzx plus LD ypx. Okay, since your ygx, this is nothing but the general solution of the homogeneous counterpart, this is going to give me 0, and this is simply going to give me g of x. Okay, so thus you can see that this expression, also satisfies the given non-homogeneous differential equation, right? And this expression as a function of x, it is called the general solution of the non-homogeneous equation. Okay, so you already know it, what it is. So I mean, if I denote it by say y capital G is nothing but ygx plus ypx, where ygx is nothing but small gx is nothing but the general solution of the homogeneous counterpart, and this is called the complementary function, and of course this is nothing but a particular integer. Okay, is it okay? Fine. So this is what is about here. Here it has already been explained. I have already explained all this stuff. So here, this is the general solution. Okay. So for non-homogeneous equations, if yp is any particular solution of the non-homogeneous linear nth order differential equation that I had written in the blackboard on an interval I, and if your y1 up to yn, they constitute a fundamental set of solutions for the associated homogeneous differential equation. So then the general solution of the equation in the interval is given by this, as I have told you. Okay, fine. And as I have told you, the general solution, it is termed as general solution of the homogeneous counterpart. It is called the complementary function, and any particular solution you designate it as the particular integer. Okay, so you have already studied it before, I guess. Okay, so so can you give me a general solution of the non-homogeneous equation? Yes. Yes. Are you comfortable in factorizing?
So please turn your camera.
Pardon?
So solution is e to the power
No.
A.
Can you see the slide?
Yes, sir.
So it is y2 prime minus 6y double prime plus 11y minus 6y equal to 3x. Equal to 3x. So can you give me a general solution of that? I see. Basically, see the complementary function is pretty straightforward, right? You simply can find it out from the auxiliary integration, right? What about the particular integral? What about the particular integral?
The minus half x minus 11. X minus 11 by 6.
Minus 11.
Minus 11 by so minus half into x minus 11 by 6.
This one?
Yes, sir.
Okay. See here the trick is like we don't have to worry about all those higher order derivatives. Okay. So you simply choose a function. Which will be
Linear ax
linear
plus
in
b.
x, which will be linear in x, something like ax. Okay. So then you know that from here, what you are going to get simply 11a. Isn't it? That's all for it. That's it. Is it okay with everybody?
So this is method of undetermined
coefficient.
coefficient.
Yes. Yeah. But even if we didn't know about it, just by intuition you can do that. Okay. So and again, you know what it is. It is something like b cube minus 6b plus b square 11b minus 6. So see minus 6 square 11 plus 1 12. So you know that d minus 1 is going to be a factor, isn't it? So how we can do that? B square minus 5b square. Sorry, b square minus 5b square. Okay. Plus 5d plus 6d minus 6, isn't it? So d minus 1 b square minus 5d. This is plus 6. Okay, so d minus 1, d minus 2, d minus 3, right? So you know what's this? Like c1 e to the power x plus c2 e to the power 2x plus c3 e to the power 3x. That is going to be the general solution part coming from the complementary function, and simply add this with that, so that is going to constitute the general solution. Okay, fine. So now, and again, this is an interesting example. So what it is asking, you have been given three functions, and you can easily verify that those three functions, they are particular solutions of the given differential equations. Okay, particular solutions of the given differential equations. So what conclusion can you draw from there? Okay, so see, whatever I have written there, whatever I have like said in that exercise that I have just switch it off. See what you got. I had three differential equations like this. Okay, where the homogeneous part was the same. Is it okay with everybody? Right? I had a differential equation like this. In that particular case, it was I was 1, 2, 3. Okay, and what it gave me that if I had, three equations coming out of this, say 1, 2, 3, right? So then I have been given something like yp1, which was a particular integral for the first equation. Similarly, yp2, a particular integral for the second equation, and yp3, a particular integral for the third equation. Is it okay? That example was something like that, isn't it?
Yes, sir.
Yes? Fine? Say, left hand side was the same, only the right hand side was different. Okay? So now, what is going to happen? What is going to happen? If I plug in something like, say, yp equal to yp1, yp2, yp3, if I operate that with LD, so your LD yp, right? So that is simply going to be LD yp1 plus LD yp2 and LD yp3. So that is going to give me what? From here I will get
G1, G2, G3.
G1x.
Yes, I am simply going to get G1x plus G2x plus G3x. Okay, so now can you give me a conclusion from this? Or let me try to make it more complicated for you. Okay, I'll make it complicated later on. But from here, what can you say? Can you give me something, some conclusion, some comment? One comment will be good enough, and based on that, I'll try to develop a theory. See, from here, definitely I can conclude that if your yp1, yp2, and yp3 are particular integrals of the equations 1, 2, and 3, right? Then their sum
linear combination
is going to be a particular integral of the differential equation given by something like this. Or the way I have done that, then their sum is a particular integral of the differential equations given by this. Say, let me call it A. Is it okay? Isn't it?
Yes.
Fine. So basically, what we can do, see here, I still haven't wrote in anything from the homogeneous counterpart. Okay, I am simply concerned here only about the particular integral part. Okay, so particular integral, whatever number of particular integral you can have for a given set of differential equations where the homogeneous counterpart is the same. So you can always get a linear combination of those particular integral as the solution of a different non-homogeneous differential equation, where the left hand side, the homogeneous counterpart is the same, and the inhomogeneous part, that is the right hand side, is going to come from the linear combination of the earlier non-homogeneous part from those three individual equations, right? So this can be put into a single theorem. This can be put into a single theorem like this. So that is what, and this conclusion will lead you to a single theorem. So this is what it is. This is what it is. See, and here say we can take any number of particular solutions. It doesn't necessarily have to be equal to the order of the differential equation. Okay, fine. Say here, say let yp1, yp2, and ypk be k particular solutions of the non-homogeneous linear nth order differential equation on a certain interval I, and in turn to k distinct function g1, g2 up to gk. Here in my case, it was g1, g2 up to g3. That is, suppose ypi denotes the particular solution corresponding to the differential equation given by 12. Here you can see that the right hand side has been designated as gix, okay, where I goes from 1 to k. Then this their sum, that is yp given by this, it is a particular solution of this one, of this equation. Okay, so that is what it is. And here simply the sum was taken. You can think about a linear combination also. You can think about a linear combination also. If you consider a linear combination here in 13, then accordingly you have to change the right hand side of 14. Is it okay with everybody? Fine?
Yes, sir.
Right? So that is what it is. Okay? And what difference do you see from this one and the one for homogeneous equations?
Linear combination of solution for homogeneous is solution, but for not in
not this one, not this one. So here the thing is that because in homogeneous the right hand side was 0, right? I mean, it was pretty straightforward. So that is why whatever linear combination you use, it is always going to be a solution of the original homogeneous equation. But here you cannot use the original non-homogeneous equation, isn't it? So accordingly, definitely you have to change it. That's it. Okay. So now, from now onwards, what I am going to do, I am going to deal with second order linear differential equations. Okay, and I am going to show you the like some corresponding theorem, and because what I'm going to do, that Wronskian part not equal to 0 for linear independent solution. So that thing I want to do. So, but prelude to that, let me just show you some more slides, and after that I will come to that. Okay. So what I'm going to do, I'm going to simply consider it in this form. Okay. So this is a second order linear equation 1. This is of course a non-homogeneous linear equation, and then this is simply the theorem A is simply nothing but the existence and uniqueness theorem for the second order non-homogeneous equation. Okay, I have already described it yesterday. Okay, fine. And again, if you plug in Rx to be equal to 0, and that means if the right hand side vanishes identically for both x, so then I get the corresponding homogeneous equation like this, and then this kind of questions I have already asked, so I don't want to spend much time on this. And then theorem B, this is nothing but the general solution in terms of complementary function and particular integral. This I have already described, and then this also you already know. If you have for the homogeneous part, if you have two solutions, then any linear combination of those two solutions is again going to satisfy the differential equation. That's it. Okay. So now what I am interested, just a minute. Yes, this is what I am going to be interested. Please have a look at this theorem A. This theorem A. See, this theorem A, it doesn't tell you anything about Wronskian, isn't it? Explicitly, it doesn't tell you anything about Wronskian. Okay? But whereas for the nth order differential equation, the linear independence or the existence of a fundamental set was guaranteed by the Wronskian not being 0. Okay? So you can see that there are two lemmas. There are two lemmas there also. Okay? So through the proof of those lemmas, that whatever we solve for nth order linear differential equation, I can also get that. Okay, fine. So y1, y2 as be linearly. Just a minute. I'll just maybe I'll get it from the book itself so that I don't have to. Yeah. Okay. So what is the theorem? What is the theorem? Okay. So you have been given this differential equation. Okay, suppose I call it 1, and I have been given that y1, y2 are linearly independent solutions of 1. This is my input, and of course, in the interval AB, so then this C1 y1x, C2 y2x, I have been told that. Then this is what? This is the general solutions, general solution of 1 on AB, right? And the next thing is important. So in the sense that every solution, of 1 on this interval can be obtained from 2 by a suitable choice of the arbitrary constants C1 and C2. Okay, fine. So what does it tell you? What does it tell you is that, see, remember one thing. Here, I have been given y1, y2 as a specific set of solutions. Okay, fine. This is a specific set. Okay, so now that I can think about any solution. I can think about any solution of this, say, yx. So what is being told is that this yx, any solution of this equation, can be expressed as a linear combination of these two solutions coming out of the fundamental set. Okay, fine. So now, if that is to happen, what must happen? Like say, if you consider, so the proof, although I am going to be using the lemma, but before that, let me tell you why the Wronskian is important here. Why the Wronskian is important? Okay, fine. So now, if I consider the existence and uniqueness theorem for the homogeneous, non-homogeneous counterpart, whether it is homogeneous or non-homogeneous, it doesn't make any difference. So what it say, if you recall, I had something like this. First, I assume that Px, Qx, Rx, they were continuous in AB, right? So then under these initial conditions, under these initial conditions, I had a unique solution of this given differential equation. Is it okay? Fine. So first of all, this one, I mean, this is just a statement I have made. Isn't it?
Yes, sir.
Right? So that means, see, here if I'm plugging Rx equal to 0, the conditions are not going to change, isn't it? The conditions are not going to change. Is it okay? Fine? So that means that if I am giving these two initial conditions, I can get a solution uniquely determined by these two conditions. And like say these two conditions are nothing but I find a solution passing through the point your x naught y naught, right? And the slope of the tangent to the solution curve at this point has a value y1. That's it. Okay. Now, if a linear combination, if say or for that matter, any solution yx, if I am able to express that as a linear combination of this, then what I must have, if I want the solution to be uniquely determined, I must have your C1 y1 x naught plus C2 y2 x naught. This must be equal to y x naught, right? And then C1 y1 prime x naught plus C2 y2 prime x naught must be equal to this, isn't it? Right?
Yes, sir.
Yes. So see, basically, what we must have, we must be able to provide two constants C1 and C2, right? Such that the linear combination coming out, linear combination like this again becomes a solution or any solution. So I must be able to uniquely determine C1 and C2 in such a way that this combination is nothing but y of x. Okay. So now, if you want to have a unique solution of this, that means if you want to have C1 and C2 uniquely determined, so then your this matrix equation y1 x naught, y2 x naught must have a unique solution, isn't it? This must have a unique solution, right? And for that to happen, I must have the determinant of the coefficient matrix. It must be non-zero, okay? And the determinant of that coefficient matrix, I can simply write it as y. Right? Okay, this determinant is given by this, and this is in fact it is simply written as the Wronskian of the functions y1 and y2 at the point x naught. Okay, so now we know that this one yeah. So if this is not equal to 0, it is possible to determine C1 and C2 uniquely. Right? Okay? So now you know the importance of the Wronskian. Any question? Any question? See, it is still all the ideas. They are still in a, like say it is in bits and tips. It is kind of fragmented. I am trying to rope in. I am trying to bring a connection to all those ideas. Say we are to prove linear independence. Okay. So firstly, what we have done, we have proved the existence of some function which is called Wronskian, right? And you have found out that if the Wronskian is non-zero, C1 and C2 can be uniquely determined, right? See here, the linear dependence and independence chain still hasn't come into existence from whatever I have told you right now. Okay, so that is where the lemmas, I'm again going to show you those two lemmas. Those lemmas are going to be important. But I was expecting some questions for you from you.
Sir.
Yes.
One lemma says the Wronskian is not zero throughout the interval. But here the initial condition depends on x naught. So at that particular point, if not 0, then it would
Exactly.
be,
Yes.
right.
Yes. So that is the question I was saying. Because say I here, if you look at whatever I have done, I am trying to prove that this linear combination X as this solution only at this point, isn't it? Are you getting my point? Right? If I could have said that it holds for all points in that interval, it holds for all points in that interval, I would have been fine. Isn't it? So the next lemma, I am going to prove that the Wronskian of a function, the Wronskian, not of a function, sorry. So Wronskian of, say, two functions in an interval, it is either going to be identically 0 in that interval or non-zero. There are only two possibilities. It cannot be at the same time 0 and non-zero. Is it okay? Fine. The next lemma that I am going to prove is this. Next lemma I am going to prove is this. If y1 and y2 are any two solutions of equation 1 on an interval AB, then their Wronskian given by this is either identically 0 or non-zero on AB. Okay, fine. See, please don't worry about it. See, I am going to rope in all those concepts again. I am going to bring the connection again at the end. Once I prove both dilemmas. Okay, so now I am going to prove lemma 1. Okay, fine. Okay, so this is proof of lemma 1. Proof of lemma 1. Okay, say the Wronskian of y1, y2. Say x I am not writing. You will understand that. So it is simply given by this. So this is y1, y2 prime, y1 prime, y2. I'm intensively writing the determinant again. I could have straightforwardly go there. I'll tell you later on. Okay. So now again, let me try to find out this one. Okay. If I find out its derivative, I'm keeping something blank here. I have a purpose behind that. So this is going to be simply your y1 fine. Okay, so eventually it is going to give me simply y1 double y2 double prime, y1 double prime, y2. Fine. Okay.
Yes, sir.
Yes, isn't it? Now from here, if I want to express this in terms of determinants, what it is simply y1, y2, y1 double prime, y2 double prime, isn't it? You don't need to worry for the time being. I know that this is this. Okay, but this expressed in terms of determinants, what it is simply y1, y2, y1 double prime, y2 double prime, isn't it? You don't need to worry for the time being. I know that this is this. Okay, but this I could have written in this form. Is it okay?
Yes, sir.
Okay.
Yes. This I'm again going to make use of this later on. So now you see one thing. Like see this y1 and y2, they will be solution of that homogeneous equation, right? So that is why what I must have you y1 double prime plus px y1 prime plus qx y1, this is equal to 0, and y2 double prime plus px y2 prime plus qx y2, this is equal to 0. Okay, so now what I will try to do, I will try to eliminate qx from these two equations. Okay, so say suppose it is small b, this is small a. So simply multiply your b by y1 and a by y2 and subtract it. Okay, so then what I am going to get, I am going to get from here. I am going to get from here your y1 y2 prime minus y1 prime y2. I'm writing it like that. Then plus px here y1 y2 prime minus y1 prime y2. This is equal to 0. Is it okay? Fine. Yes.
Yes.
Yes, sir.
Okay. Now you can see that this first term, it is nothing but the derivative of the Wronskian, isn't it?
Yes. Yes.
Yes.
This is W dash and this is
derivative
W.
of the Wronskian, right? And again, this is nothing but the Wronskian itself. Fine. Is it okay? So what happens? I am getting a linear equation, right? And you know what is the solution of this equation? The solution of this equation is simply W equal to some C e to the power minus Px dx. Is it okay?
Yes, sir.
Fine.
Yes.
Now you, I'll come back to this again. Now you simply have a look at this. Look at this term. Okay. This being an exponential function, it can never vanish, isn't it? Right?
Yes. Yes, sir.
It can never vanish. So depending on whether the constant c is 0 or non-zero, right? What is going to happen? The Wronskian is either going to be 0 throughout the whole interval AB, or it is going to be non-zero throughout the whole interval AB. Is it okay?
Yes, sir.
Yes, sir.
Yes. So
Yes, sir.
now let me connect these two. What is the relationship of Wronskian with linear dependence and independence? That will come in my next lemma. But before that, as I have told you, that being able to uniquely expressing y as a linear combination of c1 and a linear combination of y1 and y2, we proved it only at a particular point in the interval, isn't it? We determined the Wronskian only at the particular interval, and we say that if the Wronskian at that particular point doesn't vanish, then those constants c1 and c2 can be uniquely determined, right? But now you have seen that the Wronskian is either 0 or non-zero throughout the whole interval. So if the Wronskian is non-zero throughout the if the Wronskian is non-zero at a point in the interval, then it is going to be non-zero throughout the whole interval. Are you getting my point?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Okay, so now I have got this. So next thing, if I can simply prove that if the Wronskian is non-zero, then y1 and y2 are linearly independent. Or if the Wronskian is 0, then y1 and y2 are linearly dependent. My job is done, isn't it? So next lemma exactly tells you that. The next lemma exactly tells you that. Okay, fine. And but before that, I would like to come back to this again. Yeah, I think that'll be okay. I would like to come back to this again. I'll do lemma 2 from 25. see, now here, can you give me a way of finding out this C? Hmm? Can you give me a way of finding out this C?
Put the value of initial condition.
But at that point,
Sir,
where am I going to get that?
so like if Wronskian is non-zero at some point x naught, then I can find C some value which is not zero. Then from this expression of Wronskian, I can say that Wronskian is non-zero everywhere on the interval. And if zero, then C is equal to if Wronskian
If
is
zero, I don't have any problem. It is going to be zero only eventually, right?
Yes, sir.
Okay, so if it is non-zero, so generally what they do, I'll tell you what they do. They write it as something like this. That is why, I mean, they write it something like this. So this is what they call the Abel's identity or Abel's formula. Okay. Now you may be asking me, where did they get the idea from? Where did they get the idea from? I'll tell you. Like, okay. So if you consider Px, I'm going to leave it as a homework. Was it minus or plus? Okay, anyway, I can get it. Okay, so you have to simply prove that. V is a constant function. Is it? I think so.
Sin
So,
plus e to the power plus. If Vx need to prove constant, then e to the power minus x naught to x, this goes to, I think, plus. Vx is equal to wx into it, this is plus.
Plus. Yeah.
Then our identity is proved.
Yes. And from there, this idea has come. Okay, from there, this idea has come. Okay, fine. So you simply prove that this is, yeah, because eventually W, and if you write it in terms of constant, then yeah, it is going to be minus. Okay, fine. So you simply
So we can
prove that.
also put x equals to x naught in the previous equation. So
Which
from
one?
that we can simply get w equals
if it
to
is
c
constant,
into
then for any value of x, it is going to be variable,
yes,
right?
from that we shall get c equals to w of x naught.
Yeah. Okay, fine. So let me do the last part. Last part is pretty straightforward. Last part I have to prove that. I mean, if like say if y1 and y2 are two solutions of that equation on AB, so then they are linearly dependent on this interval if and only if their Wronskian is identically 0. Okay, so now this is proof of lemma 2. I'm not going to spend much time on this. Okay, so firstly, you assume that your y1, y2 are linearly dependent. So if any of them is 0, any linearly dependent, so then either of them can be 0 also, isn't it? Because any set containing a 0 element, it is always linearly dependent, right? Okay, so then your Wronskian will identically be 0. Is it okay? Because Wronskian is simply what? Y1, Y2 prime, Y1 prime, Y2. Right? Okay? So suppose Y1 is 0. Right? If Y1 is 0, then this is also 0. So eventually this is going to be 0. I don't have anything to prove. Okay? Fine. So if I assume that, suppose they are non-zero, right? So then what is going to happen? What is going to happen? If they are linearly dependent, then your y2 is going to be y1. right? One is going to be the scalar multiple of the other. So if you simply substitute it here, so this is going to give you C y1 what? Y1 prime, right? Isn't it? So this is what? Y1 C Y1 prime and Y1 prime C Y1. So this is going to give you 0, isn't it? Fine?
Yes, sir.
Right? So your Wronskian varices. They are linearly dependent. So now the only part. Say, suppose the Wronskian of these two functions, giving right. So suppose this is 0. Okay, fine. So we have to prove that they are linearly dependent, y1 and y2. So if y1 or y2 is identically 0, definitely they are linearly dependent, right? Because any set containing the 0 element is, 0 vector is linearly dependent. So let us assume that they are non-zero, right? So if they are non-zero, so definitely what I can do, if I think about this expression, so this is nothing but your y2 by y1 prime. Okay, and remember, like say, at least, see, you see, Wronskian non-zero, like say in the Wronskian, in the previous lemma we have proved that Wronskian is either 0 or non-zero. Okay, remember it is only about the Wronskian, but about the function I cannot say that, isn't it? The function can be 0 somewhere, function can be non-zero somewhere in a particular interval. Okay, so remember, like what is going to happen, that this y1 being non-zero, at least I can assume that in some interval CD, which is a subset of AB, at least it is going to be non-zero, because y1 at a particular point in this interval being non-zero, and the continuity of y1 is going to guarantee me that there is a very small interval, at least there is a very small interval C, D, which is a subset of this, such that y1 is non-zero there. Okay, fine. So this term, this term is always going to be valid in that interval. Okay, so now I have been given that the Wronskian is 0. So from here, what I get, this is going to be equal to 0, isn't it? So this means y2 by y1, this must be equal to constant, right? So that means y2 equal to some constant into y1. So that means y1 and y2 are linearly dependent. Is it okay? Fine? Isn't
Yes.
it? Right? So now we have already found out. that if Wronskian is non-zero, then they are linearly independent, right? Y1 and y2, because this is if and only. Okay, and again, at the very beginning, before the lemma, we proved that non-zero Wronskian guarantees the existence of two unique C1 and C2, right? From those two, I can comment that if the Wronskian is like say non-vanishing, then I can have linearly independent solution, and linearly independent solution mean I can always have a linear combination which is going to give you any solution being expressible in terms of that linear combination. Is it okay? Fine. Okay. So whenever you have a fundamental set, you can always express any solution in terms of a linear combination of the fundamental solution. Okay. Fine. So now let me try to do just I'll just give you one hint about how you can extend that Abel's formula for an nth order differential equation. Has anyone done that already? So I found that pretty interesting. That's why I want to share this with you. Okay. So what did you get? What did you get? Like for a second order equation, you got your Wronskian of y1 and y2. You got it to be something like c e to the power minus px dx. Okay. And this came from the fact. This came from the fact that I mean, like came from the solution of this differential equation. Okay, fine. So now you can easily verify. You can easily verify that for an nth order differential equation, if I have like say y1, y2 up to yn as the fundamental set of solutions, then I'll be interested in the Wronskian of those. And that nth order differential equation, let us assume that it is given by this yn plus your p1x y prime plus p naught x y equal to 0. Okay, fine. So now the Wronskian of these functions, it is given by y1, y2 up to yn, and then initially here I would like to I like to, is it too dark? Okay, fine. So far so good, right? Fine. See, if you recall, I found out that Wronskian of a function of Wronskian of two functions. Like say, if I take the derivative of Wronskian of two functions, it was simply y1, y2, then y1 double prime, y2 double prime. Okay, fine. Now, similarly, you can easily verify that if you take Wronskian of three functions, then it is going to be y1, y2, y3, then it is y1 prime, y2 prime, y3 prime, and then this is going to be y1 triple prime, y2 triple prime, and y3 triple prime. You can verify this at home. Is it okay with everybody? Fine? Yes, sir.
Yes, sir.
So this gives you a hint that the difference between these two rows, the difference of order in the derivative is 2. Anyway, the highest order derivative could be, like say, if we are considering 3 variables, highest order derivative will be 3. Isn't it? So now, similarly, what is going to happen? That means if I consider the derivative of this Wronskian with respect to x, then here I am simply going to have in my last row derivative nth order derivative. Is it okay? Fine?
Yes, sir.
Yes?
Yes.
So now what I'm going to see, this is the next step is very interesting. What I'm going to do, you know that the value of the determinant doesn't change if you add a linear combination of any number of rows. If you add that to another row, the value of the determinant is not going to change. Is it okay with everybody?
Yes,
right?
sir.
Yes. Say suppose I have a like say row 1, row 2, row 3, right? So if I now my new row is row 3 is row 3 plus say C1 row 1 plus C2 row 2. The value of the original determinant doesn't change, isn't it? Is it okay? Fine?
Yes, sir.
Yes. So now let us do something like this. So what I'm going to do, this row n, let me do P naught row 1 plus P1 row 2 and then up to your P n minus 2 row n minus 1 plus row n. Suppose I do this. Okay, fine. See, then let me just simply take one element. So this element, it is going to be replaced by what? Y1 prime n plus, say it has come from here. Y1 n it has come from here. Then P n minus 2, your Y1 n minus 2, right? So up to here P1 Y1 prime plus P naught Y1, isn't it? Are you getting my point?
Yes, sir.
Right? This element will be replaced by this.
And this
Yes.
is equal to minus P n minus 1 y n.
Right? Okay, from here, this is going to be equal to minus P n minus 1 y1 n minus 1, isn't it? Is it okay with everybody?
Yes, sir.
Yes, sir.
Yes, because I mean y1 is a solution of the given differential equation, right? Similarly, up to yn, they are solutions of the given differential equation. Fine. So that is why I can simply replace. You please systematically write down this at home. You have to understand it and then replicate on your own. So by doing this, I mean row transformation, I can simply write this eventually as y. And because that P n minus 1 x, that is going to be common to every A, so I can write this as minus P n minus 1 x. Is it okay? Fine, because from
Yes,
this,
sir.
from this equation you are going to get that, isn't it? Right? So that means what we have got, I have an equation is plus P n minus 1 x. This is equal to 0. Isn't it?
Yes, sir.
Which being a linear equation in the Wronskian, you can easily prove. So basically what is going to happen? This is y1 up to yn. So this is simply going to be this. Is it okay? Fine?
Yes, sir.
Yes.
Please, I mean, write it down at home. Okay, fine. So that's it. So I have graded your answer scripts. The highest mark is 7.5, and the lowest mark is non-zero. Don't worry about it. Okay. So then I will meet you next Monday. This Saturday there is not going to be any class because see, all the Saturday's classes they were extra because this is kind of a compact semester. Okay, because the month of August you have lost, so we had to, I mean, compensate for those classes. So that is why we have classes on Saturdays. Okay, so this month there are not going to be any more classes on Saturdays. So next month I think there is one class. I will let you know. Okay, fine. So I am going to meet you on Monday. Thank you.